density functional theory or quantum chemical methods to understand fuel cells and electrolysis. So I'll try to walk you through both why we choose to use computational chemistry to try and probe electrocatalytic materials and reactions. I'll walk you through a little bit of how, though I don't want to turn this entirely into a methods talk. So I will at some points just say, just point out what our models look like without going through some of the intricate details. And then hopefully I'll give myself a chance to give you at least a few different applications ranging from hydrogen fuel cells to carbon dioxide reduction, nitrogen reduction, biomass oxidation as time allows. So backing up though from the specific using quantum chemistry to look at electrocatalysis, I do like to start my talks by just recognizing why we just choose to do alternative energy research. So I give these three general guiding areas or motivating areas. The first is specifically United States centered. Our reliance on oil, which has historically been a large reliance on imports for the last 40 to 50 years. And though US has ramped up oil production over the last 10 years, still will challenge us to continue to provide the liquid fuels we need for transportation in the future. Another, of course, very pressing and cognizant motivation for alternative energy in the bottom left is the challenge of global climate change. And there I've just taken temperature sensor data that you can go on this NASA website and compared the last 20 years average temperature to a base period from 1950 to 1980. And everywhere we see orange, red, yellow is hotter in the more recent time period, showing us that there it seems to be a challenge associated with global climate change and global warming. If your monitor is pretty good, you can see some areas that are colder, but that's probably not where any of you live. So that is quite a motivating factor, but not the one that got me interested into alternative energy research when I began. It's the plot in the top right that really struck me, which was looking not just at what we do now, getting 81% of our primary energy sources worldwide from fossil fuels, but the projections that say that percentage doesn't look to change too much over the next 25 years, where you still see fossil fuels leading as our number one sources of energy. Here, this being United States data in natural gas, oil, and though renewables continues to grow, we still see fossil fuels showing up as 3 of the top 4 energy sources. So with that, we need processes that can take different primary energy sources and convert them to the uses that we use energy for every day, and catalysis will play a large role in this. So I would say my research field is catalysis. We work on heterogeneous and electrocatalysis in my group. Our heterogeneous catalysis, both both thermal and electrochemically driven, with the goal of enabling new feedstocks, whether or not we're trying to use biomass now as a primary energy source and convert that. And we've worked on a series of different projects from electrochemical biomass conversion or thermal catalysis, trying to purify gasifier effluents. And then wind and solar, if that becomes our primary energy source, electrochemistry becomes a enabling technology to take that renewable electricity and convert it to useful fuels and chemicals. Of course, we do a good amount of fossil fuel research still in my lab with the goal of using our fossil resources more environmentally friendly and with a higher efficiency. But today I'll talk to you about the work in electrocatalysis, where we're trying to engineer a catalytic material to occur at an electrochemical interface where we have a solid electrode in contact with a electrolyte where ions are going to be transferred to our catalyst surface, reactants are coming to our catalyst surface, and electron transfer, ion transfer, and typically gas phase transfer have to occur simultaneously to facilitate a catalytic reaction that then either produces electricity in a fuel cell or consumes renewable electricity in order to drive chemistry to make products or fuels we'd like to use. In any catalyst design problem or catalyst design system, we care about making a catalyst that's active and selective. So active, how fast the reaction we want to go is going to occur. And that's going to, of course, dictate the size of our device. It's going to dictate the cost of the device, and the practicality of being able to accomplish it requires us to have a catalyst where the reaction is active, fast. And then, of course, we want to be selective, have the reaction make our desired products and not make undesired products that might be an inefficient use of our resources, our electricity, or our reactant chemicals, or could also produce toxic chemicals, undesired byproducts that are environmentally or safety-wise undesired. And activity and selectivity are affected by the properties I show here, which all can boil down to molecular level phenomena that dictate our catalyst activity and selectivity, whether or not it's what we make our catalyst out of, the site composition, and for instance, I show a bimetallic where we can change the arrangement of two different types of metal atoms in order to try and facilitate our chemistry, the structure, whether or not we're on a flat surface, an edge, if we're interacting with a support underneath, other molecules, other species in an electrocatalytic environment, maybe the electrolyte, ions present in the electrolyte solvent can alter the stability of species at the surface, and the reaction environment itself all translate down to the molecular level to affect the energy involved in breaking and forming bonds. And if we want to break or form a bond here, we want an active and selective catalyst. We want the bonds we break and form to occur quickly, or with low activation barriers, high rate constants, and all of that again is affected on the molecular level by these variables. So as an engineer, I am a professor in a chemical engineering department. I think of engineering as the goal of finding the appropriate equations to then relate the outcome, the rate of reaction, the activity and selectivity to the design variables I have in my system so that I can then predict how to change those design variables to improve the catalyst. Very engineering view of what some of you might think of as scientific chemistry research. But from an engineering standpoint, if I can get the equations that connect performance to design variables, then I can predict how to change those design variables and optimize my activity and selectivity. And regretfully, if the underlying fundamental processes involved are bonds breaking and forming, the equations I use are going to be quite complicated and tedious because I need to write a separate equation for every electron involved. And those are the only equations that will be fundamentally transferable to any change I make in composition or structure. So now I have differential equations that represent quantum mechanics, or in other words, I'm solving for wave functions, orbitals, the states of the electron, and how those states are affected as I move around nuclei so that I can understand how that then connects the composition or structure to the activity and selectivity. So to give you a picture, an example of what that looks like from a DFT standpoint, we can do this first principles, quantum chemistry, density functional theory methods to study heterogeneous solid catalyst surfaces for generally two purposes. One, to explain an experiment that was already run. So try to understand why, in this case, the hydrogen evolution reaction, or I wrote here in the opposite direction, the hydrogen oxidation reaction, why platinum seems to be the best catalyst for that reaction most typically. And the y-axis here is my rate of reaction, my activity, my current density, where I can measure the rate of an electrocatalytic reaction just in how fast I produce electrons. And that's being plotted versus some property of the catalyst. And empirically, platinum is optimal. And this is an experimental plot where the x-axis is an experimental measurement of how strong each of these metals binds hydrogen. And we find that we find a volcano relationship here, or in other words, we peak with platinum having the highest activity at some intermediate value of our metal hydrogen binding energy, where too weak or too strong gives us a lower activity. So that's an experimental observation. And now we can turn to quantum mechanics and say, can you explain that to us? And then we try to translate that observation to a diagram like we see on the right, where now energy becomes our y-axis, and we're asking our computational chemistry code to give us the energy of a system of nuclei and electrons. And if the system we start with is just hydrogen in the gas phase, nowhere near our surface, and our bare surface, then that can be our reference point. So though I shift here on the y-axis, I want us to think at each catalyst, that's our reference point. And then our final product is, again, our products of protons and electrons plus our catalyst. So our catalyst is unchanged, and therefore the relative energy of our initial and final point will be the same on all these catalysts. But the catalyst itself changes how molecules interact with the surface, so how strongly hydrogen binds it. Or in other words, when I solve these equations of quantum mechanics to give me the energy of a hydrogen atom stuck on the surface of that metal, that will differ relative to reactants and products across these materials. And something that binds hydrogen very strongly might then have a high activation barrier, or a large energy input, or a slow rate to get the hydrogen off the surface and make the final product proton and electrons. Something that binds hydrogen too weakly might be very slow to dissociate that hydrogen molecule, have a high activation barrier for H2 activation in order to make hydrogen on the surface. And platinum, our optimal catalyst, gives us the optimal balance of not too fast, not too slow for either one of the two steps, and therefore the fastest overall rate of reaction. And again, our computational chemistry tools then are just letting us map out this curve. How does energy change as we bring hydrogen towards the surface, dissociate it, and then evolve it as protons and electrons when the reaction finishes? And then our goal is to map that back to a design parameter. In this case, it was composition, what we made our catalyst out of. And then we found a descriptor, how strongly does hydrogen bind to the surface. Now we can then use these same equations because they did not require the experimental data to parameterize. We can use our computational chemistry to run design experiments where we change the atoms around. In other words, convert a platinum atom to a gold atom or mix 3 different atom types together and see how that changes how strong hydrogen binds to its surface, or if it's a more complex reaction, the stability of various intermediates. And of course, we can do that quickly because all we have to do is go into a file and change platinum to gold by changing where it says PT to say AU. So we can do that quickly. We can screen, or we can just evaluate, or we can hypothesize a metal composition that might be better and get an answer relatively quickly. And this is really catalysis research in general summarized. Our goal is to understand the detailed reaction paths here. Maybe you might have hypothesized this mechanism pretty simply, but if we had, say, furfural electrooxidation, we might then, to feroic acid, there might be multiple possible reaction pathways. We're going to do detail explorations to understand what might be the energetically most favorable pathway using quantum mechanics. We can also work with experimentalists measuring different intermediates, doing surface spectroscopy, and then try to understand how to connect that reaction mechanism to the composition of the catalyst, the environment, to understand what are the key parameters that dictate performance. In this case, how strongly does the catalyst bind hydrogen? And then once we have that reduced set of key parameters, we try to then work on a design space to improve performance. So this is our overall goal, computational chemistry to connect design parameters to performance. And this is challenging in electrocatalysis. It's challenging because it's hard to make a model atomistically of what an electrocatalytic interface looks like. So this is a cartoon. This is not a result or something I can run with a DFT calculation. But this is meant to show you that our catalyst is most often a metal particle sitting on a carbon high surface area, less expensive support. That's then in contact with an electrolyte. Here drawn is a water solution, which is often what we'll be using in a lab experiment as an electrolyte. And then you can see a little tail of what might have been a polymer, just to recognize that in a real electrochemical device, we might actually have a polymer electrolyte there with ions present. This electrolyte has to conduct ions, so it's usually an ionic solution. It probably has maybe protons or hydroxides, depending on pH, and then cations and anions present. And our goal then to make an atomistic model of what's happening on the surface is going to be challenged by the fact that we have this extended electrolyte structure. We have to deal with the fact that this electrocatalyst is going to operate under a potential, or in other words, the number of electrons in that surface of the electrode are not necessarily what makes these metal neutral, but are dictated by the overall performance of the device that's passing electrons through a circuit and may pile them up on this metal surface or may deplete them, leaving the surface negatively or positively charged. That's then going to affect the distribution of ions away from our surface. And considering these in our model atomistically is going to be challenging, because if we have to use quantum mechanics to handle the rates of bonds breaking and forming, then we have to solve a differential equation for every electron. That's computationally intense. And this system, with the number of atoms I have here drawn, would probably take me months to give me back one energy. So I have to make a reduced model. Now, making reduced models is true in any heterogeneous catalysis application. So even if this was in contact with a gas phase and we knew it was neutral and not electrified, and we were willing to neglect the support, even the particle itself is going to be challenging if it's on the size of nanometers. But there's a lot of established work, both experimentally and computationally, to make model systems. Right? And we're relatively comfortable modeling a nanoparticle as thinking of it, well, it's kind of like an extended surface. But then another, but maybe that top surface is a 1-1-1 extended surface because it's hexagonally arranged metal atoms. Here we've got squares, that's like a 1-0 surface, and then we've got a step between them. And we can make various models, or in other words, we can take a surface science modeling approach to think about how nanoparticles would behave in catalysis. But that doesn't tell us how to handle electrification, solvation, electrolyte, double layer charging, or ions and electrons being involved in our reaction. So that adds additional challenges, and that is important. So I show you one result here where the same catalyst is being used under the same thermodynamic driving potential. So this is the same voltage for electrochemists on a reversible hydrogen electrode scale. In other words, we've already compensated for pH. There's the same driving force to reaction, same platinum electrode, but because we ran it in acid, the current is 2 orders of magnitude higher than if we ran the reaction at base. So that's telling us the electrolyte also affects the catalysis. And on the right, we just see that it's not a pH 1, pH 14 difference. It also occurs across the pH range. So we do need to consider how the electrolyte itself is affecting the electrocatalysis, not just the catalyst. All right, so with that, I'm going to try to show you across a few projects how we then can use computational quantum chemistry to try and attack electrochemical systems. Anytime we're trying to make out a catalytic reaction mechanism, or how the energy changes as we move from reactants to products, we are going to want to calculate reaction energies. If those were reaction-free energies, then they would give us equilibrium constants. So we want to know elementary step equilibrium constants. Of course, we want to occur. Those are activation barriers. And we'd like to then, of course, be able to relate those activation barriers back to rate constants. And if we knew the equilibrium constants and the rate constants, we'd be able to predict the overall rates of reaction with some form of kinetic model. But in our chemical system, we expect that these equilibrium constants and rate constants will depend on this variable voltage or potential, the operating system, the electrochemical potential set in our electrode by our electrolysis or fuel cell device. And that's because that potential is embedding the energy of the electrons being involved in the reaction. So if we're absorbing, say, a cation, a proton from solution onto our surface, then the energy of this electron is going to dictate equilibrium. If we made our surface more negatively charged, the energy of our electron higher, we're going to drive this reaction to the right. And we need to be able to express how that equilibrium potential depends on that voltage. And then, of course, if we're driving the overall equilibrium of the reaction to the right, we expect we'll probably get there faster. So we also expect that this electron is going to transfer faster and this rate might go up. So our rate constant might also be depending on this voltage. And I said we can absorb to a surface, but if instead of our surface, a star being what we're absorbing to, we absorb to a surface that has a species on it. So for instance, carbon dioxide, then this would be converting carbon dioxide plus protons plus electrons to say a COOH, an intermediate in that CO2 reduction. And the same type of approach is going to occur there, where instead of starting with a surface with nothing on it, we start with a surface with CO2, and we want to know the rate at which it electrons in elementary steps to get rates and rate constants to predict reaction. So I'm going to try to get through essentially 3 sections of results in my talk. The first is going to look in detail just at this equilibrium of absorption, and we're just going to use protons and hydroxides and try to show you that we can do detailed surface science-oriented calculations, match experiment, explain some unknowns in experiment, just about protons and hydroxides coming on and off the surface of platinum. I'll then talk about the implications of that understanding for the hydrogen oxidation reaction in fuel cells, and hopefully go fast enough through that to leave myself some examples where I move from just calculating equilibrium constants to calculating rate constants, and then applying that off a series of reactions. And if anybody looked before I went into slideshow mode, you saw I had probably, I don't know, 187 slides, because I just brought all the slides from all my applications. So we're definitely not going to have time to go through all of them, but I'll show you the example that seems to fit where we are in the story to start, and then I'll come back and be happy to talk about other applications during questioning. All right, so for non-electrochemists, this is probably the first experiment I understood when I went from doing thermocatalysis to electrocatalysis. Somebody said you have to know what cyclic voltammetry is. So the easiest way I think of this is let's start at 0 here on the x-axis. So we're around 0 volts. That's some energy of an electron. I've got a platinum electrode hooked to a wire sitting there in that solution. And now I'm going to add and subtract electrons. Well, I'm going to subtract electrons from that platinum surface, moving to the right. That means I've hooked it up to a device that has the ability to pull electrons out of that electrode, therefore making electrons in the electrode more stable because I'm pulling negative charge out. They're now interacting with a positively charged surface. So now that's driving electrons to go from my solution into my electrode. And what I'll see is that I get a current, and this current must be generating electrons into my circuit. And I see some peaks in that current, and that's going to be indicative of the type of chemistry that's occurring on platinum. And I cycle positive, and I see a bunch of peaks associated with something that must be creating electrons that are going into the platinum surface and then into the circuit. And then if I go back and scan in the opposite direction, I see something that looks kind of like a mirror image across this x-axis, which is the reductive current when I undo all of those processes in the opposite direction and consume electrons. And there's a lot of known, this is textbook example. If you grab Barden Faulkner electrochemistry, they'll explain to you exactly what this is, and they'll call this the hydrogen region, because what's going on here is hydrogen that was on the surface of the platinum when I started my experiment is coming off. It's going into solution as protons and electrons, leaving behind a bare surface. And then at a higher and if I ran that experiment not with polycrystalline platinum, but I ran it with a perfectly flat platinum 111 single crystal, then I would see sort of a broad feature that's underlying this set of peaks. This sharp peak would come if I ran a platinum 110 surface. That would be the only peak in this region. And this would be the only peak if I did a platinum 100 single crystal. And essentially any other parts of polycrystalline platinum can be approximated because these are the hexagons or the triangles of platinum. These are the squares, and these are the kind of rough part. And we're not going to worry too much about this region, but this is the OH region where it's thought then that water would oxidize and eventually you form platinum oxide. So to be able to then simulate or understand what's going on in this experiment computationally, I need to know the thermodynamics of hydrogen going on and off the surface. And because these peaks are relatively symmetric, that's our electrochemical proof that we can really think of this as equilibrated. Even though we're measuring a rate, a current, what we're measuring really is the shift in equilibrium. As we make this electron more and more stable, we're watching the reaction shift to the right. And at each one of these potentials, we're approximately in equilibrium. So we want to know the delta G of this process, proton in solution, plus electron in our circuit, plus surface that probably had some water on it before we did anything, then puts hydrogen on the surface, or again, if I'm doing this in reverse, take the hydrogen off by doing the reaction in reverse and create the electron. Delta G is just the free energy of products minus free energy of reactants. And now I have to use DFT or quantum chemistry to do this. And now we can start to see the challenges, because I can imagine figuring out where all the atoms are on a platinum surface. I know what platinum 111 looks like, and I can draw it. I can place the atoms. I can tell you their XYZ coordinates, but I don't really know exactly how to handle the water here. And it's not so easy now to do a proton, because I can't tell you where I can tell you where the proton is, but the water around it's going to be dynamically moving around. Getting the free energy of that, right, of that's going to be challenging. I know where to put it. I can put hydrogen on the surface and ask if it wants to absorb on an A-top site or a hollow site, but also I might be worried about how that's solvated by water. So to do a first approximation, we might neglect that solvation, but we're going to calculate the energy of hydrogen on the surface, bare surface, and the proton in water. The proton in solution is actually not as hard as we think, because we can use some thermodynamic referencing. In other words, we can put in an experimental solvation energy, and doing a quantum chemistry calculation of a proton gas is the easiest quantum chemistry calculation ever, because it doesn't even have any electrons. So we can use some thermodynamic referencing to handle that proton gas. And the voltage is actually not that hard to put in here, because that becomes our independent variable. The energy of the electron just shows up in our equation as the energy of an electron, written as charge times voltage. And there is some referencing there if you're a practitioner that takes some getting used to, but we're going to change the energy of the electron and ask how it changes delta G. Now, how we solvate does make a difference. So when I make our DFT model of a hydrogen on the surface, you might wonder, does it make a difference if that hydrogen is able to interact with water? The quick answer is for hydrogen, it makes no difference. So this is number of water molecules varying in my model versus the voltage at which that hydrogen wants to go on and off the surface. And it doesn't make much difference if I had a few waters around, and this DR method just means a lot of water. And that's because hydrogen, when it absorbs to a platinum surface, is relatively neutral. It's no longer a proton. It's more like an H in a relatively covalent nonpolar bond with the surface. But it does make a big difference if I was absorbing a sodium cation, because that sodium cation absorbs, retaining very ionic bond with the surface, retains a positive charge, big dipole moment, and that's going to interact with solvent. Now, OH might look like it has a small dipole moment, so we're not worried about that, but the OH has a very low dipole moment vertical to the surface, but still has the ability to form hydrogen bonds. So we are going to be worried about solvation. And this is just meant to show you that the actual number we calculate for what voltage OH should go on and off the surface depends a decent amount on how we solvate it. And you're going to have to trust me that I did this in a reasonable way for the next 20 slides of the talk, because I'm not going to go through the detailed models of how we handled salvation. There's definitely a plus or minus, and I'll give you a little bit of feel for that plus or minus if I can get to how we do barriers. But hydrogen on the surface, not so hard. It doesn't really interact with water. It's a very small molecule, sits down there and binds very strongly to the metal. So I can calculate then The strength of hydrogen adsorption is a function of how much hydrogen's on the surface, the coverage. On platinum 111, there is some coverage dependence, everywhere from low coverage up to a full monolayer of hydrogen. And the high coverage stuff will come off more easily. So if I started this experiment, the high coverage hydrogen is adsorbing here because it's less stable, if we want to think of it that way. As the coverage goes down, it gets harder and harder to take the hydrogen off. And I have to then make the surface more and more positively charged to drive that high coverage off as protons. And then finally, I'll get all the hydrogen off. And that's the black experimental curve. And this is our model. Our model says when you started that experiment, you didn't have a whole monolayer of hydrogen. You were already down to about 0.8 of a monolayer. And then it came off as you did the experiment. And we can match the height of the peak of this peak. We essentially get the breadth and the curvature right. And you can argue we're off by about 0.1 volts or 0.1 electron volts, 10 kilojoules per mole, which is pretty good for quantum chemistry. So now we repeat that same process on two other surfaces, 100 and 110. Some things agree very well with the experiment, like the adsorption is no longer coverage dependent. And what we see there is that we should then get sharper peaks because all of the hydrogen wants to come off right around the same voltage. And that is true experimentally, you get much sharper peaks. However, we don't get the position of them right. 110 and 100, the peaks should be in exactly the same place based on how strongly hydrogen adsorbs. We also don't get the height of them right. We actually still get them a bit too broad. So we must be missing something. And this should have been an easy question for DFT. Single crystals, simplest adsorbate you can put on a surface. And we can't get the thermodynamics of it going on and off the surface right. And that's because that process is not actually hydrogen going on and off the surface. So I don't know how many people here are long-trained electrochemists, and maybe like me, the first thing that they learned in electrochemistry was the platinum CV and the butterfly. And I learned that those peaks were hydrogen coming off and on, and that's what's in the Barden-Faulkner textbook. But our research and our DFT calculations have suggested that on 110, the OH group actually binds quite strongly. So where this region in the cyclic voltammogram on platinum goes to a current of 0, and then OH adsorbs at a higher potential. On the other surfaces of platinum, OH binds strong enough that it can come on the surface down in this range. And our DFT calculations then say 100 is about equal. Where the hydrogen comes off, OH is going on at about the same point. And that 110, on the 110 surface, the OH would actually like to go on before the hydrogen comes off. So instead, we get an exchange reaction where the proton comes off as the OH goes on. So we've reinterpreted these peaks. I can't say we're the only people who've ever done this. This is Juan Feliu's group, Detailed Surface Science, where they also suggested that though on 111, these peaks are separate, on 100 and 110, they're overlapping. And but we can use now our DFT calculations to fit and explain this and back up this experimental explanation that sort of changes the textbook understanding of what's on the surface of platinum at different potentials. So now we recognize that hydroxide is on the surface at low potentials. We can now ask, what does this have to do with the pH behavior? Because what's observed experimentally is that the 111 peaks don't change with pH, but the 110 and the 100 peaks shift to a higher voltage if we go to a basic solution. And we can explain that in terms of the fact that these cations that are present when we move to a higher pH, we do that by adding sodium hydroxide into solution. And that sodium hydroxide will actually interact and destabilize the adsorbed hydroxide groups. And that might be counterintuitive that if I put a positively charged sodium there, it's going to actually make OH on the surface less stable. And you might look at that and say, well, that's a negative OH interacting with a positive sodium. But OH on platinum is a very covalent bond. It's not very negative. It really likes to be solvated. It forms strong interactions with water. And it doesn't do that nearly as well when sodium's around, because all of that water does not want to line up and form nice hydrogen bonds. You might kind of notice that this doesn't look like the right geometry for a hydrogen bond between water and OH. And that's because that water molecule is reoriented to the sodium. So sodium essentially steals the solvation and disrupts it for the hydroxide at the surface. And now you, of course, might question if you do DFT calculations that that's a result that you'd get based on some arbitrary place I put the sodium, and the real system would have a wide distribution of structures. We spend a lot of time looking at different structures, different arrangements to make sure this result is very robust. Qualitatively, the sodium steals the solvation and disrupts the ability of water to interact with hydroxide. And we've been able to compare that with detailed surface science experiments. We can then simulate these. So the black is the experiment. This is now, we get the height, the position pretty much correct by looking at that as an exchange reaction using DFT for H and OH. And we did it again for the 100 surface as well. We then worked with Mark Koper's group, who looked at, instead of changing the because these peaks were thought to be shifting not because of the cation, but because of the pH shift. He showed that if he changed the cation concentration without changing the pH, the peaks shifted. So it really is the fact that the cations are being added that's leading to these peaks shifting, not the fact that pH is changing. And we have some nice papers, some nice DFT experiment agreement here. DFT peak potential, experimental peak potential, various cations. So we seem to know that what's going on here is that changing the electrolyte isn't really doing anything to hydrogen adsorption. There's no effect of changing this electrolyte property, in this case pH or cation concentration, on how hydrogen interacts with the electrode. All of the effect is what does the electrolyte environment do to the interaction of hydroxyl groups with the surface. And that's some detailed surface science. So hopefully I built up some credibility that DFT can be used in an electrochemical environment to understand how processes are going on. But now I want to extend that to say, well, what does that tell us about catalysis? The hydrogen oxidation reaction, I showed you this figure earlier, is thought to be predicted by how strongly hydrogen binds to the surface. And I just showed you results, in a very specific system, but that said hydrogen doesn't adsorb with a dipole. It interacts strongly with the metal. It doesn't interact with solvent. It's not affected by the change of, from sodium or the change of pH and change of cation. So if that's what dictates the rate of hydrogen oxidation or hydrogen evolution, why should the current change? Why is there experimentally a change in the reaction rate as we move from acid to base? And here I show you results for the hydrogen oxidation or hydrogen evolution reaction run on iridium single crystals versus platinum single crystals, and what we see in alkaline. And we see that there's quite a bit of difference. Actually, in alkaline, iridium is a faster, a better catalyst than platinum in base for the hydrogen oxidation reaction. And they have about the same hydrogen adsorption energy. So you can look at the coverage dependence of all these different metals, but if we zoom here and here on platinum and iridium, we see that platinum 111 and iridium 111, and those were single crystal experiments, bind hydrogen about the same. So that must suggest that hydrogen adsorption energy is not going to predict why iridium is a faster catalyst in base than platinum. There must be something else that dictates the rate of the hydrogen evolution reaction or the hydrogen oxidation reaction, both of them being faster on iridium 111. What is quite different between platinum and iridium is how strongly they bind hydroxide. So on platinum 111, I showed you hydroxide did not bind very strongly, and that was a separable high potential peak. But on iridium, down there in that hydrogen evolution reaction range, hydroxide will be on the surface. So maybe hydroxide adsorption actually is another descriptor, another predictor of how fast the catalyst is going to be for the hydrogen oxidation reaction or the hydrogen evolution reaction. So we used that. We worked with Yujong Song's group at Dalian. He varied the amount of iridium and palladium-iridium alloys and was able to get a catalyst that was faster than pure palladium or pure platinum if he had the right ratio of palladium and iridium. And we found that there was no correlation with the binding energy of hydrogen we calculated with DFT calculations. So this is DFT hydrogen adsorption energy versus the experiment rate of reaction. And if you want, you can squint. I drew a volcano in there, but if I didn't draw that, your eye would never have seen that in the first place. You'd say that's a bunch of random red dots. So the hydrogen binding energy was not a good descriptor, but here that was pretty linear in hydroxide binding energy. Obviously there's noise in these experiments, but seems to be some hint hydroxide adsorption is predicting what's a good catalyst. Here we worked with Wenjin Lee's group at Iowa State, where he looked at different forms of palladium copper, and he found that if you form the specific palladium copper intermetallic or that is a body-centered cubic structure, that we got about the same hydrogen and hydroxide binding energies as we did on platinum, and a current density with cheaper metals, or hopefully cheaper metals, price of palladium variable, that was as high as platinum. And if we start putting all of the known data for the hydrogen oxidation rate in base onto something that looks like a volcano, I think those 4 points, you'd look at me and say that makes a pretty good volcano for the experimental rate of hydrogen oxidation plotted versus how strongly we bind hydroxide on these 111 surfaces. And that, if you're very convinced by this, I'm worried I can sell you just about anything, because any 3 points I could have drawn a volcano for. So I've got 1 point that happened to fit, if you want to look at it that way. So 4 points can't convince you of that type of relationship very well. Now, if we start adding other single crystals of platinum, seems to be filling in, some noise, and I'm still only on one side here, but not too bad. If I then also just change the electrolyte from lithium, sodium, potassium, and cesium hydroxide on a polycrystalline platinum, still looks like it's forming a bit of a volcano. So hard to have perfect proof there, but there does seem to be some indication that hydroxide adsorption potential is predicting the hydrogen oxidation rate in base. My student who did all this work, and I'll show you in his picture in a couple minutes, it was Ian McCrum. Ian, when he graduated, went and did a postdoc with Mark Coper and joined his group. Before Ian got there, they were thinking, well, we've got this adsorption, we've got this hydroxide adsorption effect, but maybe they're just effects of the same phenomena. I told you salvation, the interaction with water was very important to dictating hydroxide adsorption, and that the cations were messing with that salvation. And Mark's group proposed that maybe what's also happening here is that when we go from acid to base, the ability of water in general in the interface to move is really what's changing. In other words, hydroxide binding maybe isn't the descriptor it's a descriptor, but it's mechanistically not really linked. They're just two different features of measuring how water is behaving at the surface. But Ian, and once he joined Mark's group, brought those two thoughts together, and they just had a Nature Energy paper come out late last year, where again, they did a nice, careful set of experiments where they just changed the presence of another metal atom at a step of platinum. And they showed a nice volcano between the current density and the hydroxide binding. And then they combined that with DFT calculations that did have activation barriers, and essentially explained this as the rate determining step. Depending on how strongly hydroxide binds, the rate determining step can be the water dissociation. And water dissociation at the surface in alkaline is what gives you the adsorbed hydrogen, making an OH group on the surface. So how strongly OH binds is directly involved in the rate determining step for weak binding metals. For strong binding metals, OH desorption coming off the surface becomes the rate determining step in being able to evolve hydrogen, and therefore OH binding is mechanistically tied. And then they use this to say, well, that's true under some pHs and some conditions. So we really still need these two descriptors, hydrogen adsorption and hydroxide adsorption, in order to dictate what would be the rate determining step. And with that, then we get a volcano. So I hope you see coming out of the screen here, this height is the best catalysts. The highest rate catalysts are at the top of this two-dimensional volcano now with two descriptors. This gives us additional levers now to make better hydrogen oxidation or hydrogen evolution catalysts. We don't just have to play with the metal. Now, of course, Ian's results, the best, the nicest indication of this on the previous slide, did do this by depositing a second metal at a step. But you could also do this then with electrolyte cations, and I showed you that earlier. Perturb the OH binding and then perturb the hydrogen oxidation rate. And you could, in general, use salvation interactions to play with the ability to dissociate water at the surface. So surface additives, organic molecules, different solvents or mixed solvents, all possible ways to alter hydrogen evolution or hydrogen oxidation. So with that, I've left myself on the order of 4 or 5 minutes maybe to talk about kinetics. So obviously, I'm not going to get through all these different applications, and I didn't expect I would. But I'd never like to talk about an electrocatalysis without saying it's important with DFT to think about rates of reactions and activation barriers. And I didn't show you any calculated activation barriers, at least not from my group. I did mention that Ian did them. We've spent a lot of time doing method development work in my group about how you could calculate an activation barrier and for proton and electron transfer reactions, or essentially ion electron transfer reactions. We develop a thermodynamic framework that lets us do something that resembles more a hydrogenation barrier, adding hydrogen to a molecule, but then referencing it back properly to the reactant state, and then modeling and then getting an activation barrier that can then be extrapolated. So it's calculated at 1 voltage, but then can be extrapolated to give you the barrier as a function of voltage. A lot of work going on in my group, and I hope the publications that will be coming out this year are going to spend a good amount of time trying to understand how important are the various method choices we make in dictating those activation barriers, because I see a lot of papers coming out with activation barriers now. But I do think it's very important to recognize the amount of plus or minus involved and how this is modeled, and give some best practices. Here I show you just whether or not when we look at that transfer, we're forming an NH bond here on a rhodium surface. The involvement of water, we can have that H3O plus transferring that proton. We can put 2 water molecules in there. We could put more explicit waters. That doesn't seem to make much difference, but we can then add a continuum solvent, a dielectric media around here. And we see as we add more solvation, the barrier does seem to be coming down. I don't know that a dielectric constant of 78 for water is right, but this seems to suggest it's very important to look at both explicit involvement of water as well as the long-range salvation at the electrochemical interface. And we're looking at approaches in my group as well to develop to model that. It's also important to recognize that there'll be an electric field there, and that surface will have a charge on it. So each one of these lines has a different assumption. These are all with 2 water molecules. So we've all recognized here that's an H5O2 plus involved in transferring that proton. And we change the assumption of whether or not the surface is charged, whether or not we apply an electric field, whether or not we go through a full control of the voltage. And you can see if I look at 1 voltage here again, I get an activation barrier that varies from about 0.4 eV down to about 0. So the previous slide showed you that explicit salvation and implicit salvation can vary the barrier by 0.4. Here I show you that essentially the electrification model can vary the barrier by 0.4 eV. I should highlight these are not additive because there's salvation had to be in here because when we electrify, we then often also have to salvate. But they are somewhat additive. So barriers can vary on the order of 0.6 eV based on the approach used to calculate them. With that, we've still been able to use computed barriers to help us understand a number of different applications. The one I can zoom through the fastest is the borohydride electrooxidation. So I'm going to use that as an example to show you real quick how we might then look at kinetics in a more complex mechanism. Many of you might not be familiar. It's not a very popular electrochemical reaction to look at, but the reaction is to oxidize borohydride with 8 hydroxides in a basic solution in a fuel cell, giving you a cell potential as high as 1.64 volts to borate. And if this gets you confused seeing a B there because we don't work on boron all that often, just make it a C, and then that looks like methane goes to carbon dioxide. So it's an electrochemical cell that essentially oxidizes something that's relatively equivalent to methane in electronic structure, but it has a negative charge because we moved 1 to the left in the periodic table with the boron instead of the carbon. So it's water-soluble methane. It would be great if we could use it as a fuel. Borohydride is not widely available, so it's not great in an overall electrochemical energy efficiency sense, but it is a nice device to give you a high-density fuel in a fuel cell. And we have looked at catalyst development for this reaction. And the reason I bring it up is because I want to convince you that we can look at complex mechanisms that aren't hydrogen going on and off a surface. So this starts all the way at a BH4 anion in solution and ends all the way at that borate. And we actually also looked at the hydrated borate as products. And we get a number of elementary steps, but if you can calculate activation barriers, then you can see how these rates vary with voltage. This is all on the gold surface. This agreed pretty well with what's seen experimentally. No current at -1 volt, where some of these barriers are pretty high, pretty good current density around 0.2. We can actually take every one of these barriers, put it into a microkinetic model and predict the current as a function of voltage. And we agreed pretty well with experiment doing that. There are some assumptions we had to make about transfer coefficient. I can get those lines to line up perfectly if I make the right assumptions. And then this is one example where my lab was successful in designing a better catalyst. We then looked at how can we balance the fact that we need to bind the borohydride a bit more strongly, but not too strongly, because if it dissociates too easy, you get a competitive hydrogen evolution reaction. And we computationally predicted that a gold copper bimetallic surface would have about 1/4 volt shift. And then we experimentally measured about a 0.17 volt shift in improving the electrocatalysis with gold copper for borohydride oxidation. And again, I'm going to have to hit page down quite a bit now because I didn't want to, I knew I wouldn't have time to walk you through doing the same thing for carbon dioxide electroreduction, where we can map out those reaction energy diagrams, DFT calculating barriers, look at how cations are involved, put that in the model, try and explain how they change the CO2 reduction energetics, look at ammonia, which is not a pretty story from our results because all these barriers are really big. You see a lot of 1 EVs showing up there for barriers. So this is, essentially coming back and telling us why it's so hard to electrochemically reduce ammonia on late transition metals, but we can look at how electrolyte might get involved. So how we might then use some additive in the interfacial region. In this case, this was a peptide bound to the surface to try to accelerate.
Could be me.
Mike, we've lost you.
No sound.
The timing on temporarily losing my internet connection there went very well, right at the end of the talk. So I plan that just to give you a break to let that sink in. But hopefully I've convinced you that we can do detailed single crystal type work with DFT. We can use that to help guide us into thinking about how the electrochemical interface affects the kinetics, either in hydrogen oxidation or looking at more complex chemistry. There's still a lot of work to do. I really think there's a lot of
What's going on? Again, we lost him.
Hello, everybody. If you have questions, you can unmute yourself to ask, or you can type into the chat box. So hopefully Mike comes back soon. Oops. Can everybody hear me?
Yeah, Louise, I can hear you.
Oh, okay. Yeah, so you can either ask the questions and then I will pass to Mike. You can type it or ask by unmute yourself. Yeah, how we simulate free electrons. And also we can have a kind of a group discussion. So anybody has question can feel free to comment. So I will pass a question from Dr. Tang, how we simulate free electrons in software, for example. So when Mike is coming back, we'll ask him. Yeah, I'm recording all the questions and then pass it to Mike. Yeah, sorry for this.
No problem.
Yeah, we don't have your, yeah. You can unmute yourself, yeah. When we are waiting, so I make another announcement. We are going to have the 6th monthly invited talk on the February, let me see, the last Friday of the February 26th. So we'll have the 6th monthly invited talk. And then I will inform everybody the link so you can join us. And also the division, energy and fields division is going to collaborate with the catalysis today to publish a special issue. Anybody wish to publish your paper, your results, feel free to contact me. So I think we have Dr. Alan Chaffee, so who will be our chair for 2021. Oh, Mac is here. Hello, Mac.
Hello, I'm back on my phone because my home internet seems to have picked a very good time to go out right when I was about to get hard questions.
Oh, sorry, no problem.
So if I can get back on my computer, I will. But otherwise, you know, the phone is a little bit harder to use my slides or to chat, to use the chat function. But if people were to ask questions orally, I'm more than happy to answer.
Hello, Mike. I just typed the question for you.
Yeah, so my phone, I'm not quite as savvy about using the chat function.
Okay.
Let me see. All right.
Do you want me to read? Do you want
Yep, so
me
I
to
see
read?
it. No, I see it. I just finished reading it. So the yeah, no, so I mean, there's a lot of very good work on electrocatalysis of platinum nickel alloys, various effects that nickel can have. The question mentions cage structures, and I'm not sure, I'm not as aware what they mean by that work on cage structures. and they mentioned that platinum dissolves. So there's a lot of questions embedded sort of in the same thing there. Platinum nickel HER, there's like some nice work that shows that the oxidation of nickel that can occur on the surface of platinum electrodes has very similar effects to what I mentioned here in terms of cations coming down and interacting and changing the water structure and the charge at the surface. I've seen both Jeff Greeley's work computationally and Mark Hoper, Longfellow have done surface science type work that nicely shows that. As far as the dissolution challenges, and of course the alloying platinum nickel can affect hydrogen binding. I think it's more interesting when you get into that sort of metal oxide mixture in the hydrogen with nickel and what that does. As far as dissolution, I think of Dane Morgan's work computationally is really looking at platinum dissolution. I know it's been a few years since he did that, but he's a good enough scientist that I didn't spend nearly as much time trying to look at platinum dissolution. But dissolution is the opposite of the deposition reaction I wrote there. So if I'm looking at cation adsorbs, then cation desorbs would be dissolution. So calculating the free energies associated with that and how maybe platinum at a step can desorb is definitely a tractable problem with DFT. I haven't spent as much time looking at it, and of course, it's a slow process relative to the catalysis. Other questions?
I think there are two more talking about how do we simulate free electrons in the software. For example, in VASP. Yeah, I'm not so sure because I'm not.
Sure.
Yeah.
So, in my case, looking at the thermodynamics, for somebody new to this area, I would point you to the early 2000 Norskopf group work on the computational hydrogen electrode. That's kind of a nice place to start. And Gerber and Siener at MIT at the time also did nice work just generalizing, that helps you generalize that to lithium ions or any ion. Using a thermodynamic referencing approach to handle the energy or the chemical potential of the electron. How to then simulate it, to put that electron and watch its movement within a calculation is much more challenging. And, I mentioned our work, and I think our references can help somebody start thinking about barriers, and activation barriers do require you to think about, the movement between reactants and products, but we don't really simulate the dynamics. I mean, how to make a movie of the electron moving would be quite challenging because it would require representing, the whole, not just the interface, but really you start then getting into the device and where does the electron come from. That's challenging to simulate. All right, and I see that there's something else in the chat. Let's see if I can read that. So somebody asked, is there a way to calculate the potential dependent barrier that other than the extrapolated method? Yes, so it's not as clear in the literature. We've kind of adapted what others have done using the VAFSOL approach. But in a model where you are electrifying, where you actually change the amount of charge in the metal surface by changing the net charge on the electrode, which can be done as long as you also can maintain the neutrality in your model by putting the opposite charge somewhere. So that's where I say electrification. The VASP-SOL additive in VASP also has the ability to put a Poisson-Boltzmann distributed countercharge on top of the surface. So now you can put a charge in the surface, put a countercharge, you can change that charge, and you can see how that changes the activation barrier, the character of the transition state. So there you don't have to extrapolate. You are really evaluating the transition state at different voltages. I have some concerns with it. Once you put that dielectric media, I found the sensitivity to how you handle the continuum solvent and the countercharge is incredibly high. So I'm not sure to what degree that's adding a lot of value. The way we seem to be heading towards is to just apply an electric field. Most DFT codes let you turn on a field, and it's really the same effect. And then there's, of course, how do I relate the field back to voltage, which requires you assuming a double layer model, which feels like a bad assumption, but you were assuming that also when you used VASP-SOL and turned on the Poisson-Boltzmann distribution. So either way, you've got to end up assuming a countercharge. And I really like just putting an electric field in there and then assuming a Helmholtz model. I think it's simpler. You understand more what's going on. And then you can calculate how the barrier changes with field. And you're not extrapolating now. You're calculating barriers at different fields.
I think I have a question. Sorry, I sent it to Jimbo a direct message, not to everyone, so you cannot see it.
Sorry, you can ask. Yeah.
Yeah, I think for the study of electron catalysis here, so we need only consider the ground electronic states, so DFT is enough. Is there any case that we need to consider like excited electronic states? So maybe DFT not enough, you need to use TDFT. Is there any case like that?
So, with the metal surfaces in electrocatalysis, you're looking at charge states. So you are, if I thought of the neutral ground state, the perturbation that's occurring is adding and subtracting charge, not exciting, right? So there isn't an application there that I see. Photocatalysis obviously changes the voltage. It changes the energy of the highest electron by exciting an electron, and there, you do need the excited state. Photoelectrocatalysis then couples that, right? Because you allow that electron to go into a circuit. So if you're not using the excited state directly, you may or may not need to use DFT and look at an excited state. What I'm trying to think in my head is if moving the electrode from being a metal to an oxide, in some case, then essentially forces you to model an excited state, but it's still a charged state. So not intrinsically, no. So I would say no. I mean, in electrocatalysis, we're generally working with ground states of various charge, not excited states.
Okay, great, thanks.
And I saw another question in the chat about the importance of a local field. I do think one big open question in electrocatalysis, whenever we think of the modeling and most of the discussion talks about essentially what I would call the average field, right? An electrochemical double air model, a Helmholtz model, a Stern model, a Gouy-Chapman doesn't give you a distribution. It gives you a distribution of field as a function of distance from the electrode, but it assumes that in the surface plane the field is equal, which is not really a valid assumption, right? I mean, there are definitely local fluctuations as ions and electrolyte adjust, and their relative importance in catalysis, I think, is not in electrocatalysis not very well established. We've looked at reactions and tried to find ones where we thought the electric field was going to make a huge difference. And we generally find that you have to move the voltage quite far to get a variation in field that's big enough to make a very large difference in the activation barrier and the rate of reaction. Things like moving by a volt might get you a field effect that's worth an order of magnitude in rate, and that's for the most extreme cases we can find. But yes, I think there's a lot of open questions in the importance of a local field. And when you start thinking about a transition state has a big dipole because its electron and ion are still separated and being transferred. So electric fields should have a big effect on that. And those electric fields also affect the ability of solvent to organize and reorganize, which is part of ion transfer as well. So I think there's still a lot of open questions in the relative importance of local fields.
How about, I do have a question. Maybe related, may I ask now?
Yes, please.
A question about what's the status of tribochemistry and dynamics of surfaces? Is that at the stage where it can be modeled?
So you can correct me if I'm wrong. I'm translating that to what degree the tools I've talked about, computational quantum chemistry, are useful in tribochemical studies.
Correct. By extension of what you're doing, because there's some catalysis or some reactions, surface reactions, even polymerization is talked about in the literature. But as far as modeling, is that what's the state of the technology or your experience with it?
Yeah, so I can't say that I'm well versed in the field of tribochemistry enough to know what people are doing today in modeling. We did one study with Song Kim at Penn State, who would call himself a tribochemist now almost 15 years ago. Where he was adding different gas phase molecules and seeing how those affected the tribochemical, friction measured at the surface through adsorption of those molecules. And, obviously everything I showed you could be used to look at adsorption, right? You could then, if you look at breakdown of surfaces, right, even if that breakdown is being caused by mechanical force, by friction, you can use the same approaches I gave you to look at the activation barrier associated with breakdown, right? If I'm breaking a silica surface or SiO2 surface, which is what we worked on back then, I've got to break silicon oxygen bonds, and I can look at the barriers associated with those and how they're perturbed by various surface treatments or structures. When I think of the field of tribal chemistry in general, I mean, my naive look at that thinks of it as, I'm putting grease or oil there to remove friction. That gets you on a much larger length scale than the big molecules, multi-layer adsorption. And there DFT becomes quantum chemistry becomes challenging to just meet the length scales you're talking about. And I don't know. So I would guess most of that work would be done with more, approximate atomistic methods, force fields and molecular dynamics, not DFT.
All right, thank you.
No problem. At least I'm going to look in the chat.
There's one more question, Mike, for you.
How to estimate the effect of both anions and cations when the potential changes from positive to negative. Right. So anions and cations can come in through specific adsorption effects, meaning they're directly on the surface and chemically interacting with it. And the tendency for an anion or cation to adsorb, of course, as I showed you with the proton, as a cation absorbing, its tendency to adsorb changes as you change the electrode, the potential. So if I was thinking about very low potentials, reduction potentials, I'm more worried about cations. If I'm going up to more oxidizing potentials, I might be more worried about anions. And that's why the oxygen reduction literature, high potential, spends a lot of time thinking about whether or not the electrolyte is absorbing, whether or not my naphthion is solvatable enough to keep my sulfate off the surface, et cetera. And why now, if I think about CO2 reduction, I'm thinking more about the cations because it's a negatively charged surface and they're closer. So obviously what voltage you're at might make you concerned about which anion. And of course, there's going to be cases where both anions could be interacting in the surface. Then of course, there's if I know the surface charge, that ion creates a field, right? So there's two ways to think about the ion effects: specific, what's going to be near my surface, and do I need to think atomistically about what it's doing to the stability of other species? And then globally, my field will change direction as I move. And how does that, I can just think of the ions as point charges that are creating a field. I showed you ways to put them in. There was no reason everything I did with a cation could not have also been done with an anion. And we have some papers on sulfate and was it acetate absorption? I'm trying to remember that. Formate. So we've done sulfate and formate absorption and how that changes with voltage. So there's definitely interesting work in those. And I think anion and cation effects in electrocatalysis it's still got a long way to go in understanding, and providing and understanding how we can use them to our benefit.
Any other questions for our speaker, Mac? Any other questions?
Mike, I've got a question for you.
Oh, please.
Sure, please.
Yeah, are you effectively saying through quantum chemistry, quantum mechanical design, you can design a catalyst for a specific product in the chemical reactions space?
So we have designed catalysts by using quantum chemistry to either provide understanding if you understand chemically how a catalyst affects a reaction, that understanding can be used to make rational choices to make a better catalyst. So there are cases where that understanding, so for instance, I showed you the borohydride, the fact that we understood from that why gold was active but unselective and why platinum was, so gold was selective but inactive, platinum was active but not selective, and if we found something that had the right property intermediate of those two, gold, copper, it was better, right? So that, and I would say that was rational, right? We were able to look for a specific property. There's also quite a bit of work of just screening, right? If I know hydrogen binding energy and hydroxide binding energy, predict what's a good catalyst, I can do a DFT calculation on 1,000 different alloy surfaces and tell you which one might be better. I have a student who literally does that in selective hydrogenation reactions, where she's currently looking at thousands of intermetallics and screening ethylene and benzene binding on them. I can't tell you that screening process has helped us yet, and it's a new project in our area. But we're not the only ones to do it. Sort of mass screening of catalysts for binding of adsorbates. So I think in heterogeneous catalysis, quantum chemistry, DFT is density functional theory being the flavor most people like to use, has become an essential tool. Really, most productive research projects are integrating that with experiment to facilitate rational catalyst design.
Okay, thank you.
No problem.
Any other questions for our speaker? Any other questions? I assume the silence meaning no. If anybody still have questions, you can email to me. I will pass them to Mac. So let's give Mac a round of applause. Thank you so very much, Mac. Yeah. And
Thank you, everybody.
Stay safe, stay healthy. So let's conclude today's talk. Thank you.
Bye.
Sorry, I do have one question for the recording of our meeting today.
Uh,
We